The topic for this video will be stellar luminosity and brightness. So we will be covering what is a black body, what is the Wien's displacement formula, what is stellar luminosity and stellar brightness. Let's start off by describing what is a black body. The official definition is, a black body is an idealized physical body that absorbs all incident of electromagnetic radiation regardless of frequency or angle of incidence. Okay, this might not make a lot of sense at first, but let's try to break this down. It says here that a black body absorbs all the light and energy that hits it. So light can do three things when it hits an object. It can reflect off of it, it can transmit through it, and it can get absorbed straight into the object. For our black body, it can only do one thing, which is absorb. It would not reflect or transmit light. So let's write this down. A black body absorbs 100% of light and energy that hits it. Now, it says here that it's an idealized physical body. What does that mean? It means that a perfect black body does not exist. All objects on Earth and in space either reflect or transmit some amount of light. So this is a theoretical object that we're talking about. So let's write down, a perfect black body does not exist. However, we can have approximate black bodies like stoves, stars, heaters, and these behave like black bodies, but they still reflect some amount of light. You've probably seen a stove getting red slowly and slowly. This is happening because it's absorbing energy, and a black body does the same thing. When it absorbs some electromagnetic radiation, it starts to produce something from itself. This emission is called a black body radiation, and this consists of temperature and a glowing light. Let's move on to how we can apply this mathematically. If you look up black body, this might be one of the first images you'll see. A graph that has intensity and wavelength. The wavelength is in nanometers, which is basically 10 to the power -9 meters. And intensity is kind of like the number of photons coming out of the black body. What this graph is showing is that objects where this is an object, this is an object, this is an object, and this is an object, they emit a spectrum of wavelengths. So we could have a star that emits all these different wavelengths. However, all those wavelengths come at different intensities, and all the points here, 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 and here show which wavelengths have the maximum intensity. So there's a German physicist that came up with a law for this, and the relationship goes like this. The maximum intensity for the wavelength times the temperature equals a constant 0.002898 Kelvin meters. So if you're given the maximum wavelength, you could just plug that into this formula to find the temperature of the star. Or if you're given the temperature of the star, you could plug the temperature into this formula and find the maximum wavelength the star emits. Let's look at an example. We could get something like, our sun emits radiation with a peak intensity at a wavelength of about 0.5 micrometers. This is 10 to the power -6. So what is the temperature? So let's write down what we're given. We have that the maximum wavelength is 0.5 micrometers, which equals 0.5 times 10 to the power -6 meters. We want to convert this to meters because our formula is in meters as well, Kelvin and meters. So now that we have our wavelength, we can plug this into our formula. We have 0.5 times 10 to the power -6 times temperature equals our constant 0.02898. Let's solve for temperature. And my calculator is giving 5,796 Kelvin. What's the actual answer? So the temperature of the sun is around 5,780 Kelvin, which is very close to our answer. So you can see that the formula works pretty accurately. Now let's go on to, what is the maximum wavelength of a star with a surface temperature of 6,440 Kelvin? Now let's do it the other way. We're going to have to plug in the temperature, which is 6440. And then we're going to set this equal to our constant. And now we can just divide both sides with the temperature. And we'll get 4.5 times 10 to the power negative 7 meters. If you want to convert this into nanometers, because that's how it's usually written, as nanometers, we can convert this into 450 nanometers. And that's our answer. So pretty simple. Now what can we do with the temperature of a star? This brings us to our next topic, luminosity. So luminosity is referred to as the total energy outputted by the surface of the star. So let's write that down. And the formula for this is L, luminosity, equals 4 pi r, which is radius of our star, squared, times the temperature raised to the power 4 times the Stefan-Boltzmann constant. If we know our radius and the temperature of a star, we can find out the luminosity, which is in watts. The Stefan-Boltzmann constant, which is this value right here, this is 5.671 times 10 to the power negative 8, and the units are watts per meter square, Kelvin to the power 4. That cancels out with the meter square here and the Kelvin to the power 4 here, giving us just watts as our final value for luminosity. This diagram clearly breaks down this formula here, where the total area in square meters, the surface area of a sphere is 4 pi r square, right? So we're trying to cover the entire surface and see how much the entire surface emits, total energy outputted by the surface of a star. So that's where this part of the formula is coming from. Now the energy produced by 1 meter square, that is the Stefan-Boltzmann constant times temperature to the power 4. And from that we get the total energy produced is energy per 1 square meter times the total surface area, giving us our luminosity formula. Let's try an example problem to practice this formula. So if our sun had a temperature of this much, we got this from our last problem, what is the luminosity? And it says the radius of the sun is 6.96 times 10 to the power 8 meters. This is the general symbol for solar radii. So if you see that symbol anywhere, like for example, if you get a problem with 2r with that circle, know that they're trying to describe a star that has twice the radius of our own star. So let's start plugging into our formula. So we have luminosity equals 4 pi r square times t to the power 4 Stefan-Boltzmann constant, which is 4 pi. We have 6.96 times 10 to the power 8 squared times the temperature, which is 5796 Kelvin to the power 4. And the Stefan-Boltzmann constant is 5.671 times 10 to the power negative 8. Let's plug this into our calculator and we'll get our luminosity as 3.895, or 6 if we're rounding, times 10 to the power 26 watts. So this is our final answer, and this is the luminosity that our sun emits. Now let's move on to flux, which is also referred to as brightness sometimes. Flux and brightness generally mean the same thing. There's a minute difference where flux is more quantitative and brightness is more qualitative, but I'm not going to go too deep into that. Just know that different sources might refer to both of them in different ways, but they both mean the same thing. Here, if I say flux, I mean brightness, and if I say brightness, I mean flux. I'm not going to make a big difference here. So the definition of brightness is the amount of energy per unit time that reaches a given area from a star. So let's write that down. The formula for this is very simple. So the brightness equals the luminosity of a star divided by 4 pi distance from the star square, which you can also write as 4 pi r radius of the star square, temperature to the power 4, Stefan-Boltzmann constant, divided by 4 pi d square. If you don't right away have the luminosity of the star, you can just plug in the radius and the temperature. The handy thing about this formula is that the 4 pi and the 4 pi at the bottom cancel out, leaving you just with a cleaner version of the formula. Radius square, temperature to the power 4, Stefan-Boltzmann constant, divided by distance from the star squared. This diagram might help show the inverse relationship with the distance, where we have divided by d squared. So feel free to look at that if you want. But let's move on to an example problem. What is the flux of the sun from the surface of the Earth if the sun is 1.496 times 10 to the power 11 meters away? Again, let's use the formula. So we have brightness of the sun equals luminosity of the sun divided by 4 pi d squared. The luminosity, we already found it in the previous problem. We'll just use 3.896 times 10 to the power 26. So we have 3.896 times 10 to the power 26. And this is watts, divided by 4 pi d squared, which is 1.496 times 10 to the power 11 squared. From this, we have watts on the top, and we have meter square on the bottom. So one thing I forgot to mention, our formula should always give units in watts per meter squared. But let's plug this into our calculator, and we should get 1,385 watts per meter square. And that's our answer. This is the brightness of the sun that we receive from Earth. So today we talked about what is a black body and what this definition really means. We talked about Wien's displacement, how you can relate the maximum intensity to the temperature of a star. We talked about the luminosity of a star, which is the total energy outputted in watts. We defined the Stefan-Boltzmann constant. We talked about flux, which is not at the star, but from the observer, and it depends on how far the observer is from the star. And we went over example problems for all of these topics. I'll see you in the next video. As always, thank you so much for watching. The notes that I used during this video is linked in the description for you to refer to and use in the future. And please be sure to check out the rest of the videos in this series. I'll see you in the next one.